presentation deck. Give me a moment. It's coming through. Dinesh, how are you doing? Show up your face. Dinesh, show up your face. I want you guys to show up, so that we have more engaging conversation. I can get the feedback from you or no, whether you're able to listen or not. Okay. I think here, yeah, complete notes. Okay. So we are moving into the next topic, that is the machine learning and AI topics. Very fascinating. All learning things are fascinating, okay, for me. But nonetheless, take a look at this example. Okay, so this is what we are going to do: machine learning and artificial intelligence. Artificial intelligence is a subset of machine learning. Okay, there is a lot more stuff to do here compared to machine learning. Machine learning is just the learning part of it, but this is the interaction part of it also. Okay, so it's a subset, and somewhat overlapping areas. I don't know. People say it's a subset. I don't think it is purely a subset. So if you look at everywhere, you will see the relationship between machine learning, artificial intelligence, deep learning, and learning methods. Learning methods includes machine learning and statistical learning, and they always say artificial intelligence is a subset of machine learning. But machine learning is just a learning method. Artificial intelligence is not only the intelligence coming out of machine learning, but also plus interactive intelligence. Okay, that is a very different thing. So in other words, the machine knows how to respond to you, how to interact with you intelligently, but it uses the knowledge from machine learning. So my definition of artificial intelligence is that the human senses, what are the different senses, human senses we have? Touch, see, right? Once I know I'm not seeing. Okay. See, hear, touch, 3, smell, 4, eating is 5, right? The taste, 5. The 6th one is 6th, that's why it's called 6th sense. Okay. So machine learning is only the 6th sense. What about other things which you need to interact? Okay. Intelligence is not enough. Just if you have show up your face, guys. I'm serious. I'm telling you seriously. Show up your face. Okay. Unless you tell me, that oh, my broadband is pretty bad, and I know you're going to say it. Those who are very shy are going to say that. Okay. Of course, others who are truly facing that also will say that. But anyway, just hang in there. Interact with me, talk to me. So I want to change the delivery method also. I want to create the question in your mind, little simple questions, and then you ask me the question. That's a better way of engaging than just dumping the knowledge. Am I getting along with you? Am I making sense to you? Dinesh, are you there? Can you show up your face? Abhinesh. So I want you to, I want you to engage. I'm trying to get there. That is, little questions on the way I should raise. Or if you don't get it, you will get it on your own also. So I said the difference between machine learning and artificial intelligence makes sense to you all, right? Where machine learning stays. Machine learning is 6th sense. But what about other senses where it collects the data? Touch is a collecting method. Seeing is a collecting method. Okay. And the other things, 5. Okay. So that is my take on artificial intelligence. Artificial intelligence is machine learning 6th sense plus the interactive intelligence. You can write it if you want. Artificial intelligence is machine learning plus the interactive intelligence. Interactive intelligence, all the senses. Okay. Now here is the common example. All right. You haven't seen my shared my screen. Okay. I'm going to share my screen. Here's a common example. The common example that is published by McKinsey. I have references for these things. Don't worry about it. Okay. There are 3 beautiful, simple references that I'm going to share with you. Modeling type, cheat book with more technical details on the taxonomy of statistical learning, machine learning, and AI. Okay. So Read this one, an executive guide to machine learning, a high-level taxonomy of methods useful for interview, an executive's guide to AI, a high-level taxonomy of methods useful for interview. Okay, so please, use this, use these references that is in your third slide. So here is the example. This is given by McKinsey. Maybe today it is not there, but I know there is a pathway to achieve this in statistical learning. Okay, but anyway, so if you have all these data points here, there are, depending upon the density of points here, these are all the, the either the hills or the bottoms. Usually, you can say it depends. These are called ISO curves. Have you heard of ISO curves? Anybody? So here is the method. Here is the reason I want to see you. Okay. Do you know ISO curves? I'm saying, anybody knows about ISO curves? ISO curve. Please write down that word, ISO curves. Write down that word. Anybody knows ISO curves? Dinesh, Abhinesh, Anirudh Yushamurthy. ISO curve in a three-dimensional world, especially a geographic world, it's the same height. ISO means same. ISO curve means same height represented by a curve. So if you go to a hill, the same heights are not on the same level. It's not like a cone, right? Cone is, all the curves have the same height. All the points on a curve have the same height, right? But instead of saying all the curves on a point have the same height, all the curves each curve may have a different height at a different point. Am I making sense? Because a hill can be sloping like slowly here, fast here. So if you take at a height, okay, if you take a slice of a hill, if you take a slice of a hill, you will have same height, but in a slice of a hill, but what we do is, we represent the slice to be the height at each point. Am I making sense? So in other words, if you slice a hill, in one point it may be higher, around the circumference, another point it may be lower, 2 feet lower, right? Isn't it? The same from the same surface, from the bottom of the earth, not the bottom of the level earth, from level earth to that point may not be exactly same height. Am I making sense to you? That's why, we put 1 feet, and the next feet is, and the same feet on the right may be a down, or right may be up, right? So that is what the ISO curve. ISO curve is supposed to represent. ISO curve is supposed to represent the height in a geographical sense. Please search for the word ISO curve. In land measurement, it is very important. For example, in general, the geography and maps, these are all very important. So my point is that both based on the density of the points, the blue is, here it's a blue color, here it's a red color. Do you see that? Do you see that? It's a red color here, red color here, red color here, but here blue here, red color here, right? So blue is, let's say, the blue, you can interpret anyway, but let's say blue is the height, that means more the height you get. No, the way it is actually, the way it is done, it is blue means is going bottom, but that's what I see it. Okay, so red means height. Okay, red means higher, blue means, level curve, more and more level curve, level to the earth. Okay, so here, a lot of points are here. From the data point of view, this is a lot of points are here, less points are here. Agree with me? A lot of points are here, less points are here, a lot of points are here, lot more points are here. Relatively speaking, less compared to this one, and then here it is not that much. Everybody gets it? Okay. So this is this is one way of representing 3 dimensions. That's the point. So it's one way of representing 3 dimensions. Third dimension is the density of points here. Okay, it's like a bubble chart. Okay, and the point here is, does this make sense that the curve has to be like this? If you build one curve, regression curve, it will be like this. Agreed or not? If you build one regression line for the whole data, this is drivers A, drivers B. That means, you know, the factors here, if you want to call it, you know, factor A, factor B, just if you use factor A and factor B. Agreed? Just two factor alone. This is the intensity of the observations. So one regression, if you build using two factors, two variables, factor is same as variable. One regression, if you build, it will be like this, because it has to come towards more of these points. Okay, less of this point, because there are less points here, more points here, more points here, but then this is pulling that. Does it make sense intuitively? This is published by McKinsey. This is a management company, the world, the topmost management company. Okay, so this regression makes sense, correct? But what they are saying is that regression is an averaging process for all the observations. But if you take this region alone, you can select one, you know, the graph will be like this, the graph will be like this, the graph will be like this, okay? Graph will be now here. These are all region split, okay? I'm not sure. You can do that. Basically, what I'm saying is, no, it's a kind of decision tree. Okay, 1 second. Oh, joy. Decision. So these are all decision tree, basically decision tree. Okay. Each region belongs to a tree segment. Is everybody here? No response. Okay. Right. These are all, you know, different regions. Each one refers to some kind of an averaging process. So your decision tree will be different values will have different values you'll have different values depending upon the segment of the drivers A and drivers B. Get it? The only two people who are showing their face is, you know, Anirudh and Ishramurthy, and I'm going to talk to them. Okay. Do you guys get it? Can you repeat what I said? Repeat what I said, Ishramurthy and Anirudh. Anyone?
So you are taking 5 segments based on where the drivers are, and then you are
density of the observations, the density of observations, right? Yeah, go ahead.
Yeah.
6 segments are there actually.
So based on the density of the observations, you have made these 6 decision segments, and then that part I was not.
That average value is what we are predicting.
Yeah.
Because so I didn't say that sentence. Okay, go ahead. Sorry. No.
So within each of these segments, we are going to average and then predict. Is it separately?
That is correct. The process is there could be any other metric, but average is the most common. All right. So if you have, let's say these are all, you know, let's say these are the people who are having diabetes. Okay. It tells you percentage of diabetes. If it is a continuous variable, it is the average value. If it is a discrete class, it is the percentage. Right? There are 6 segments. Yeah. In each of these segments are in a closed range. That's all you need in a closed range. Oh, you can actually have more segments here, but those are all less number of observations, right? So what are the other one? I'm going to show you. You can actually predict where I'm going to put this one, right? Do you see this one? That's another one, right?
Yeah.
That's another one is coming. You can see that there are more things are coming, right? I'm sorry about this. It keeps moving. I don't know what I'm doing. It keeps moving. So there is another one here, right? So this is what the decision functions are doing. And we are going to talk about that momentarily. Okay. Everybody gets it? Of course, I can't see the other people. So I'm going to ask you guys. Everybody's good?
Yes, sir.
Good. Okay, excellent. So this is not regression now. We are talking about, you know, small areas of the data space. Okay, now I'm talking multidimensional data points, right? Small areas of data space where what those average values are or what those percentages are. If we can model that, we are doing a better job. That is the point, they are saying, right? And that is what the decision tree, random forest, boosting methods are about. Okay, and also neural network is about. Deep learning is all about. Your deep learning methods are basically neural networks. Everybody thinks that neural network is good enough, you can solve all problems. There is actually a understanding that universal deep learning creates a universal solution, universal function approximation, which is same as solution. Please write it down. Neural networks can create universal function approximation. Very important statement. Please write down, Anirudh. Okay. Deep learning, neural networks, which is the foundations of deep learning, it can create universal. It is a universal, not it can create. It is a universal function approximation method. Get it? Supriya, correctங்களா? It's very important. You also hear these things. Okay. It is a so நான் பார்க்க முடியாது எனக்கு. I cannot see what you write. Okay, this is the reason why I'm asking. Sometimes when it's the conversation. என்ன சொல்லுங்க.
இல்ல வீடியோ ஷேர் பண்ணேன். I can, if I turn on the camera, I can't go on the.
That's okay. You are hearing me, right?
Huh?
You are hearing me. Respond to me, okay?
Yeah.
All right. So Dinesh was asking, how is this different from? Once again, I thought he asked that question. Interesting question, right? How is this different from clusters? So that's a very good question, guys. Think about it, and everybody think about it, including Dinesh, right? So what is that? In the cluster, what is meant by cluster? I don't know. Did I know? Do I know? Yeah, I did teach you, right? When I say I don't know, whether we know together. I did teach you cluster analysis. Yes or no? Yes or no? You have to say, I don't know.
We covered that.
Yeah, we covered that, right? So I'm going to see the picture. We covered that. So what is the most important difference between the cluster analysis and which is the unsupervised algorithm versus the supervised algorithm? What is the big difference? Why it is called supervised versus unsupervised? This is going to be, I want to create this kind of conversation, this kind of kindling your thought, catching your brain, action, thinking and so on. I want to change the process. It's not just to dump the knowledge. It doesn't work. So talk to me and interact with me. What is the big difference between supervised algorithm and unsupervised algorithm? Please go ahead, jump. பேசிட்டே இருக்கணும் என்கிட்ட. என்ன தினேஷ் டைப் பண்றாருன்னு நினைக்கிறேன். தினேஷ் இல்லையா? KNN எங்கேயோ போயிட்டாரு. KNNலாம் போயிட்டீங்க நீங்க. Yeah, K nearest neighborhood. That's a good one. K nearest. What is K nearest neighborhood? K nearest neighborhood. Is it supervised algorithm or unsupervised algorithm? That's the kind of question I'm asking. K nearest neighborhood points, right? நான் மறந்து போச்சு உங்களுக்குலாம். I actually, when I started the course, I did teach you what is meant by supervised, what is meant by unsupervised. Come together here. Come and focus here. Okay, forget about this course. What is meant by supervised algorithm? Forget about everything else. I'm just, let's kindle our thoughts. What is meant by supervised algorithm? KNN is supervised. Okay, thank you. So why? KNN is supervised. What is the special thing about supervised versus unsupervised? நீங்க சொல்லணும், நீ engage பண்ணணும். See, one word at a time. Try. It will come to you.
So supervised data, you have prior data on which to build the model.
What is the prior data here? What is meant by prior data? That is, we know the outcome. We know the outcome. Outcome is your dependent variable. Everybody gets it? If the interview or a question by say, Kepan, chumma kepan. They'll just ask, oh, what is meant by supervised algorithm? Just say it. This is the most fundamental thing. You know the outcome. In the unsupervised, you don't know the outcome. But you are trying to develop knowledge as some kind of an outcome, even though you don't have any outcome. So when you cluster points, you are saying these points are looking like men, these points are looking like women, these points are looking like children, these points are looking like villagers, these points are looking like daily wagers. You understand what I'm saying? No knowledge, but we are developing knowledge there. Of course, different type of knowledge. Every algorithm gives you knowledge, but it's a different type of knowledge. The knowledge is basically outcome. We're trying to figure out. Label. We are trying to find out the label. We know the labels in supervised algorithm. Please write down these sentences. These are very important. You should know whenever I say keyword, write down your, at least write down at the time. You see why I need to see the picture? I know what you're doing or what you are not doing. Enna Dinesh, correctங்களா? Abhinesh. Okay. So this is a collection of points, but Dinesh mentioned, he didn't ask that, but I think he meant that, is this KNN? Am I correct, Dinesh? I think that was the point you wanted to say. Is this KNN, right? It is a KNN here, right? In this case, around this neighborhood, what is the mean? Or around this neighborhood, okay? That's what. So it's you can say KNN here, okay? All right. Unsurprised, the learning path is not trained. Learning path is not trained. Very complicated sentence. Okay. Unsurprised means no outcome. They are to train the algorithm. No outcome used to train the algorithm. That's the way to say. Supervised means outcome is given to the algorithm to train, to learn from. Outcome is given, for the algorithm to learn from. Okay. So does this picture make sense to you, everybody? Okay. Does this picture make sense now? This is more powerful, isn't it? Because this one curve is not averaging for everything. That is an attempt. It's in the simplified model. But here it is kind of taking for every one of those small areas of application. It is giving a perfect answer. You cannot beat this solution by this average solution. Do you agree with me? You cannot beat this solution, all these differential solutions that is relevant to that area of application. Area means physical area I'm talking. You cannot beat that by an average curve like this. That is my point. Average curve like this. Isn't it? Makes sense, right?
Yes, sir.
That's somebody, yes, sir.
Anirudh.
Oh, Anirudh. Okay, sorry. I couldn't see your movement of the face. Okay, thank you. That is the main point here. So the whole idea of decision tree, the whole idea of boosting, whole idea of random forest, all these things are doing like this, segment wise. Small areas, what is its solution? What is its applicable outcome? Outcome values are. Okay. So we are going to learn decision tree, which is the basics, which is the basis for random forest. A forest is a collection of trees, so you have to know the trees. And a forest is a collection of trees. And then there are methods to improve the trees and the forest. That is called boosting methods. We're going to see some very sophisticated methods, and that is our purpose now. On top of it, we'll also talk about Adaboosting, gradient boosting method, Adaboosting method. We will talk about those things. And extreme boosting method, 3 different boosting methods. Adaboosting, gradient boosting, extreme boosting. Okay, 3 different methods. We will talk about it, and then we will move into what is that? These are all solutions. Neural networks. We are going to talk about neural networks, which is the foundation for deep learning. We'll talk about. We will not just talk about train ourselves using neural networks. Also, what is called the supervised. What is called the SVM, which is support vector machine. SVM, we will talk about SVM. We will learn about SVM solutions, support vector machines. We will learn, and then we will go into deep learning. Okay, there is a lot to learn, but there is only so much we can do, right? In this, 28 hours, So, but nonetheless, we will cover very important topics, very basic foundations as well as important topics, and then we will apply them for unstructured data, image analysis, and also we can touch on NLP, a little bit of NLP we can do. We will do also what is called the reinforcement learning, okay, which is a very different type of learning, reinforcement learning. So all these fascinating topics we are going to do. That is our purpose in this course. Okay. So let's start with the decision tree. All right. So we are talking about the decision tree. Let's go into the decision tree. Did I teach you decision tree or not? I kind of introduced logistic regression. At that time, I talked to you about decision tree, right? Do you recall? Okay.
Yes,
so
sir.
Yeah, let's review that quickly. Let's review that quickly. Let's do this. I want to get into Google Drive, IOA, academic, ML. It's not an ML. I want to show you this small video. It's not a video. It's basically a MP4 file without a voice. Okay. I want you to note down few things when you see this. What do I mean by that? One second. So I'm going to share with you LR animation. Yeah, LR animation is fine. So I'm going to share with you this one. It's also a review of few things. So just to watch this one. Correct? I will actually, I have posted this in public domain also. So some message is coming. Sir, I got some network issues. Can I turn off my camera? That's fine. Okay, support vector machine, fine. Okay, you guys turn off, that's fine. But try to show your face, because I think you have to get to that level. We are not very lucky to see your face regularly in a three-dimensional real world, but at least in the virtual world, we should know the feedback from each other. But anyway, you can switch it off, that's fine. So I'm going to give you this. This is a 23 megabyte file. I don't want to give it to you, but go to this link and then watch that, okay? Okay. Let me play this and tell me whether you are able to watch, okay? And I'm going to open with the movie, Windows Media Player, movie, TV, search, choose another. Let me do this, Windows Media Player. So there are 10 points, 8 points which are, no, 10 points are negative and 10 points are positive. Okay, 10 points are negative and 10 points are positive. This is a story about people buying insurance, health insurance. So the points are distributed around the age, okay, in this way. For the negative cases, we have 3 of them after 43, age 43. For the positive cases, we have 6 of them after age 43, okay. So what this means is, stop this, okay, I'm going to go back a little bit. Okay, I'm going to stop here. So this is the scatter plot for qualitative response variable. So remember this. This is the scatter plot for qualitative response variable, right? And this scatter plot tells us there are 3 points above age 43 among the non-buyers. These are the buyers, these are non-buyers. Okay, the y is equal to plus means buyers, y is equal to minus means non-buyers. This is the age. The x-axis is the age. Okay, and so among the 10 buyers, only 6 of them are above age 43. But on the other hand, non-buyers, only 3 of them are non-buyers after above age 43. So looks like 43 is a good cut decision rule. Above 43 means they are buyers. You can say like that. Above 43 they are buyers. Below 43 they are not buyers. Does that make sense? That is the decision. So instead of seeing this as the we can build a logistic regression like this, but I'm interpreting it only as a decision tree. Okay, I am interpreting it only as a decision tree. So you might wonder why you split here. Maybe you can split here. If I split here, there are 4 non-buyers above age, let's say 38. Above age 38, 4 non-buyers. But on the other hand, buyers are 80%. 2, 2, 4. 2 to 4, 4 plus 4 is equal to 8, right? Among this, at this point. Are you with me, guys? If I say the decision rule is to cut at age 38 to tell us that above age 38 they are buyers. If somebody makes the decision rule like that, that decision rule is not a perfect rule. There are errors there. There are 40% of them are non-buyers, but 80% of them are buyers. Are you with me so far? And this is where we get all the true positive, false positive, true negative, false negative, right? Okay. So this division like this is what is called a decision tree. Okay, you are dividing it at this point. But where do you draw the line as the best possible cut? Which means that the errors, the false positive and false negative are the errors, right? They are minimal. That is the best place to say to cut it. Are you guys with me now? Are you folks with me? So the way to achieve this, there are many ways to achieve this. One of the method is what is called the information gain approach. We are going to talk about that. Information gain approach. Okay. So information gain approach is the method I'm going to use. So let's go to this presentation deck. So I'm going to teach this information gain method using a interesting example, nice example here. Are you able to see this one example? So in this example, I have 12 observations, totally 12 observations. 6 of them are people who are willing to wait at the restaurant, and 6 of them are people who are not willing to wait at the restaurant. So you can see that this is what the target variable is. Will wait is true. T means true, that means they will wait. F means no, not true, that because it is false. So how many T's are there? 1, 2, 3, 4, 5, 6, right? So the remaining F, 6 of them are F. So there is an F here also. Okay? So 6 people wait, 6 people don't wait. That's our sample. But these are our variables about the sample. So this is a supervised algorithm because we have this outcome variable values that is helping the algorithm to learn from, supervise the learn, whether it is learning is good or not. Now there is these are the variable. What are the variable? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 attributes. In computer science we don't say the word variable, we say attributes. Okay, so those are the 10 attributes. What are those attributes? Alt means is there an alternative restaurant nearby? Is there an alternative restaurant nearby? Bar means is there a bar inside the restaurant? Okay, so and then this Friday means is it a Friday? These samples, is it when they took this sample randomly, are these sample Friday? So the first sample who is actually waiting, right? The first sample is willing to wait, but there is an alternative restaurant nearby, but nonetheless he is willing to wait. He is not saying that no, okay, I'm going to go away. And then bar is there is no bar inside. Okay, so even then he is willing to wait. Okay, because if you have a bar, people have a tendency to wait, right? And then the next one is Friday, right? Is it a Friday? No, it's not a Friday. Okay, if it's a Friday, there is some dynamics about waiting time. Okay, and then is he hungry? Is he or she hungry? True. So even though he's hungry, he is willing to wait. Okay, that is how I'm interpreting everything. And then are there patterns in the restaurant or not? There are some patterns at that time when the visitor comes. Okay, when there is no pattern, people will not, I don't know, there is a tendency, if there is nobody is there inside sitting and eating, people will not wait. That is more likely not wait. I don't know. Okay, if the price is very high, they will not wait, isn't it? Everybody gets it. So triple dollar means pricey, single dollar means inexpensive, double dollar means medium price. Okay, and then is it raining at the time? If it is raining, they will more likely be waiting actually because they don't want to go in the rain to another restaurant, right? So, but on that day anyway, it was not raining. And then is that a restaurant? Is that particular restaurant sample has to reserve? And in this case, yes, he did reserve. If you reserve, you are more likely. Okay, so that's what it is. But all these variables do not mean you can see that, for example, this is a personal information, pricey, right? If it is pricey, he's still waiting, right? But some people, if it's pricey, oh, okay, it's pricey, it is. I'm hungry, it's pricey, let me go to another restaurant. I cannot wait. Okay, no, he did wait. He or she did wait. And the last two variables are estimated time. He knows what is the estimated time. So it's zero. The person who is at the at the receiving end, receiving person says, you have to wait, a maximum 10 minutes. That's what it says. Oh, okay, he is waiting. If the person says 60 minutes, will he wait? Most likely not. Okay, but where did I get this most likely information? I know in practice most likely. Okay, so this sample is supposed to represent most likely, right, information. So this is and then it's a type of food is French. If the French food for fascination I have reserved it, I'm not going to leave easily. I'll just wait even though there is no bar there. Are you with me, guys? Do you understand how to interpret the data? Do you understand how to interpret the data? Okay, thank you. Now, this is a multi-dimensional decision tree situation, isn't it? Is this also a decision tree? Whether the decision is whether somebody who is coming to a restaurant, patron who is coming to a restaurant, or visitor who is coming to a restaurant, will he or she wait or not? Very simple problem, only two-class problem. And you can build a logistic regression also here too. Even though all variables are class variables, you can do that. But we are here to learn today the decision tree. So we are going to use what is called the information gain method. Okay, by information gain I mean we are going to use what is called the definition, what is called the entropy. Entropy is the measure of uncertainty. Information is the measure of certainty. Please take it that way. Okay, nobody defines information very clearly. Most of the time people don't define. I'm defining it here very clearly. Information is the opposite of entropy. Okay, entropy is the measure of uncertainty. Information is the measure of certainty. Okay, so if I have two class variable, yes or no, true or false, wait or not. So what we are saying is that if you listen very carefully, if you have a very certain information, very clearly it's going to happen information. Okay, how many bits are needed to store that? Can you tell me the answer? Somebody guess what it is? A bit is a yes or no. A bit is a yes or no. A bit means, that is the meaning of bit. Bit means it's a state yes or no. One binary notation, 0 or 1. How many binary notation I need if I have very, very, very certain information? That means it is yes or no. Only one bit. Agree with me? One full bit I need. Okay. But if I don't have very certain information, I have some intelligence, okay, then if I can devise a measurement process, which captures the reduced amount of bits needed. I don't need the full bits, I need only partial bits, because I have not intelligence, some uncertainty is there, because full certainty means 1 bit. Okay, full certainty means 1 bit. The maximum uncertainty is this can happen, that can happen, both ways, 50%, 50%. Imagine these three properties. Okay, full uncertainty means, full certainty means I need a full 1 bit. Full certainty means I need a full 1 bit. And maximum uncertainty means it can happen 50% this way or 50% that way. Okay, that is the maximum uncertainty. Okay, so if I can devise a measurement which captures this information in an inverse way, I'm putting a lot of complicated things here, in an inverse way, then it's a good measure. So what do I mean by that? And we can use that to measure uncertainty. Look at this one. Okay, so if I have full information, either it is 0 or 1, okay, I need 1 bit, but I need 1 bit, but I'm going to take an inverse function, which means I need 0 bit, and I need a full bit, 1 bit, where I have the maximum uncertainty, which is 0.5. It can happen this way or it can happen that way. That is the maximum uncertainty that happens when the probability of the event is 0.5, and I need a full 1 bit. If I can devise a function that ranges between this and this, 0 to this is the number of bits. Okay, vertical is number of bits. These are all points, 0, 0.1, 0.2, 0.3, like that. Okay, 1.0. So if I can devise a function that represents this information, this is what is called the entropy function. Such a function is called entropy function. Somebody brilliantly devised that function, and that is called this function, HPQ. P is the probability of success, Q is the probability of failure, right? In this case, probability of waiting, probability of not waiting. So that function is negative of P log P to the base 2 plus Q log Q to the base 2. You might be wondering where in the world this guy invented this kind of very funny looking formula. Yes or no? Yes, uncertainty means you can say impurity of data. Yes, that's another way. That's another way of saying it. Yes, but do you get what I'm talking about? What is an entropy function? This is what they call the entropy function. Okay, everybody gets it. Which is the purpose of that is it will measure the uncertainty in the data, impurity in the data. Okay, and it is the inverse of having knowledge about, because perfect knowledge means you don't need inverse, I said, right? So that's why it is, you are talking about you don't need any bit there, you don't need any information, there is no impurity there, there is no uncertainty there. But the maximum uncertainty happens when it is 0.5. Do you agree with me? The maximum uncertainty happens when the impurity is the maximum when it is 0.5. So these H bits are for uncertainty. That is correct. The number of bits, it is actually measuring both uncertainty and uncertainty, right? Because here we are talking about in this, let's take a look at this one. When we have the certainty of the event, we are talking about 0 bits are needed. You have to be very careful how you interpret it, right? When there is a certainty is that P is equal to 0, absolutely it's not going to happen. And I don't need any bits to store. If P is absolutely going to happen, that is this extreme, the other side. I don't need any bits to store. But I need 1 bit to store if it is the maximum uncertainty, that is 0.5. And I want that kind of function to be defined. And that function is defined here. You get it? How the kind of inversely I am talking about it. Everybody is good with what I said. It's a very important function called, entropy function. Now, so if I have probability, that's what I'm telling you, right? I'm going to show it to you in calculation. The P is equal to 0.5. For an event, it is 50%. Happening, 50% not happening. Then the entropy is P is 0.5. Put this half here, because P is half, Q is also half, which is 1 minus P. So half log P log half to the base 2, half log half to the base 2. So you can say it is, this is half, so log half to the base 2, basically, because it's a half log to the base 2, is a half log to log half to the base 2, half log half to the base 2. So basically this half and half goes away, so only log half to the base 2. But this is same as log 1 to the base 2 minus log 2 to the base 2. Agreed? Okay. When you have the ratio, that's what it is. Okay. Everybody is good? All right. So, but then log 1 is 0. So we have minus half, and then another minus half here, because the 1 will become 0. So it becomes minus 1. And because it is, I already took that minus 1 here. If I don't take it, then it becomes minus 1. So because the function is defined with the minus, so it is 1. Everybody gets it? Okay. So what did I show? What have I shown now? It's not just now. There is a function called, entropy function, and that entropy function is useful to measure uncertainty in or impurity. I think Yeshwamurthy said it good. Impurity in the data, and so I call it as uncertainty in the data. So the information gain, that is the certainty gained. Okay. Entropy is about uncertainty. Information gain is about gaining certainty. So entropy, so what we are going to do is we are going to keep dividing the data from more information, more data to segments of data where we have more gain, information is gained, more information is gained. So for example, in that restaurant data, we have 6 people who are start with this, 6 people who are waiting, 6 people not waiting, and then we look for each of the variables. There are each of the attributes, 10 attributes are there, right? For each of the attributes, I'm going to see where the certainty is, and I will take that, because we are trying to predict. That means we are trying to get in the direction of certainty. So each variable, I calculate information gain, which means I'm calculating certainty gain. I'm calculating, where it is more predictable. So information gain, I am calculating the following way. So given the variable, in this case, whether the patterns are waiting or not. Okay, the patterns are waiting. Are there patterns in the restaurant or not? When you see the restaurant, when you go to the restaurant, you are checking whether are there patterns or not. Okay, so there are 3 cases. I know there are some patterns, none patterns, and full of patterns. There are 3 different possibilities, right? But it so happens, if you look at the data, and watch this data very carefully, you have to review this data yourself. Okay, so the pattern sum is how many? 1, 2, 3, 4 patterns. But then it so happens four cases of sum, right? 4 cases of sum. Okay, and you can see that all the 4, this is true, this is also true, he is waiting, here also he is waiting. Some case, all of them are waiting. That means all of them are blue. Okay, none case, 1, that is failed, F, none case, one more, none case, yeah. So you can see that 2 of them are none case, 4 of them are some case. Perfectly, these are all predictable situations. Are you with me? But here, in the case of full, there are 4 non-waiting people and then 2 waiting people. 2 people are waiting here, 4 people are not waiting here. In this case, when they see full of patterns inside the restaurant, when they see full of people inside the restaurant, only 2 people wait, 4 people do not wait. But in the other cases, either they are waiting completely. If it is a sum, they will completely wait. If there are none, nobody will be waiting. That's what the sample is saying. For that case, nobody is waiting. For this case, all of them are waiting. But for this case, 2 out of 6 are total 6. Okay, 2 out of total 6 are waiting. 1/3 of them are waiting. So I calculate this kind of, take this information, put it in this kind of formula to find out what is the information gain, what is the gain achieved from the original 6 people. By using this information, what is the gain in the certainty is achieved. I do the same thing from the original split of this 6 and 6 versus 6 versus 6. What is the gain achieved here by using this attribute, the food type? Depending on the food type, I find out the same thing. But here you can see that there is no gain is achieved. Here it is a 50% uncertainty, 50-50, right? Here you can see 50-50, 50-50, 50-50, 50-50. Do you see what I'm talking? There is no gain. It is 0 gain achieved here. Do you understand what I'm saying? Okay. Ishramurthy says yes. Okay. Anybody else? Okay. So 2 people, 3. Okay. Okay. Dinesh, you are saying, it's a great idea to say your words in incremental proportion, like this, right? But the terminologies have to be used the way I am using it. Okay. It is important that, you articulate within yourself, utilize your articulation should utilize what you know, right? I'm not just talking about incremental proportion here. I'm talking about information gain. So please say information gain, isn't it? And if you don't know how to use that word, then you have to learn that part of it. So this is where articulation comes. I want to ask you guys, repeat this. Actually, I want to ask that guy. And there is nothing wrong. I suppose there's nothing wrong, but I don't know. Am I making sense? Anirudh, Abhinesh, and Ishramurthy, as well as Dinesh. You have to start using the phrases the way I use it. Otherwise, you will continue to use your way. This is not about incremental proportion. There is no incremental proportion. So again, you are using a lot of words, Dinesh. Okay. You will have tough time because if you don't internalize the phrases the way I am saying it, it's going to be tough. You know, it will be confusing. Even with this, unless you repeat it again and again and again, it can be confusing because a lot of things I said, the information gain versus the entropy, why I say that it is, the gaining the information is inversely, connected to the uncertainty in the observation. How we measure the maximum uncertainty is happening at the way the formula is constructed, the maximum uncertainty is happening at the middle, not at the end. The ends are most certain cases. So, we don't need any bits to save information there. But you do need bits in the computational sense that, you need maximum bits when it is a maximum uncertainty, which is 0.5. This terminologies, you have to use it, the phrases, you have to use it the way I say it. Please try that. In fact, I want you guys to talk to me back. I want to ask the question. So can you repeat what I say? Does it make sense like that? No, I want to engage you guys. But anyway, all right. So, we have to calculate that kind of computations for every one of the variable, and the variable that has the maximum information gain. That means it is picking out the maximum certainty in prediction. That is the one that we are going to introduce as the first among 10 variables to create the decision tree. Do you get it, everybody? So can you tell me what the strategy is? Can somebody, I want to hear from each one of you, but you don't even show your face. Anirudh, you want to say the way I said it?
Sure. So from what I understood, you have number of factor variables which are available. So you want to see which one will reduce your uncertainty the most. So in this case, this food variable which you took, it does not play any role because the same uncertainty with which you started French, Italian, once you segment, also the same level of uncertainty is there.
Which means
but for variable,
there is no gain. There is no gain. Yeah, excellent. Go ahead. Wonderful. Keep going.
Whereas for patrons, there is some level of reduction in uncertainty which we have got. So in whichever variable there is a maximum reduction in uncertainty, we'll go ahead with that to build the model.
As a starting point, right? As a starting cut, as a starting decision tree. Okay?
Yeah.
Okay. Excellent. So, and Ishwarmurthy very nicely said, oh, is this the same as impurity? Uncertainty, you can call this if you want, impurity. Okay, less and less impurity. But I think information gaining certainty in the direction, and so that we can predict more certainly, is a better way of thinking about it. Because people use impurity, see, this is the issue, right? People have their own ways of confusion, they will import into it. I'm not talking about Ishwarmurthy, but literature says that as impurity in the data. It's not an impurity for me. You can't use it for prediction. If there is no certainty in the information. That's a better terminology. Okay. All right. So this is very good, right? So all of you gained, beautifully summarized by Anirudh. Okay, wonderful. Thanks a lot, Anirudh. I pick on you only because you show up your face and you are willing to talk. And it's a good thing. Okay. So don't feel bad that I'm picking on you all the time. Now, so we apply that, so there is a 1 bit needed. Remember that, because it is equal observation here, there is 100% uncertainty there. So you need 1 bit for that, because maximum is when it is 50%, right? 50%, right? So it started with 1 bit, and then you are eliminating the number of bits needed in the new attributes. Every attributes I'm going to compute like this, compare with the original uncertainty, and here I am able to reduce because of the uncertainty. This is the uncertainty amount here. It is, if I remove that, there is so much information is gained. So this much certainty is achieved. Are you with me, guys, now? How this measure is a meaningful, useful measure? Get it? And I have only 2 people who constantly respond to me. That is Anirudh and Ishwarmurthy. Okay, I want everybody to participate. Okay, thank you. So you can see that I just use how do I calculate these numbers? H01. This is the probability of the event. See, there are 2 events. In the case of this is 2 events, right? 2 out of 12. That is the probability of that event, and that event I get 0 gain. That is not because there is 1. I need 1 bit here. I'm sorry, 1 bit, not 1 bit, 0 bit here, 0 bit here, 0 bit here. But here is more, some bits are needed. That is calculated to be this amount. That is, 459, 459. Okay, this 459. So 1 minus 459 is 0.459 is 0.541. Okay, so you guys will be able to calculate. I will give you a workbook there as part of this one. You can see that. I think you can click on that. I will post this ML notebook, okay, for you. Okay, ML notebook for you, and you can calculate and verify yourself. Okay? So this is 0. Nothing is there, nothing is there here, because this is 0, 0 times this is 0, this is 0, 0 times this is 0. But this one turns out to be some number, and that value calculated by this is weighted by this, half weighted by this one. Okay. This turns out to be around 8, 0.8. So it becomes something around 0.459. So 1 minus 0.459 is 0.541, but here is 0. So if I compare only these 2 attributes, this reduces the uncertainty. The original uncertainty is 1 bit of, 1 bit is needed, but now it is reducing it, by 0.459. So, this compared to this is a great starting point to cut the, create the decision tree. That's what is happening here. Everybody, among the initial is patterns, and then the none pattern, some pattern, full patterns, right? And that ends up entering into the model. Are you with me? Why this variable entered first? Because if you try all the other variables, it turns out all the other attributes, it turns out this is the maximum gain. Are you with me? Okay. Probability of yes and no is that, which one you're talking about, this probability of yes and no? Oh, you mean the weights? These are called the weights for the entropy, right? These are called the weights. Yeah. They are probability of that event. Yes. Okay. So probability of that event times the you can say, instead of probability of that event, you can say probability of that. This is the uncertainty in the class, this particular class, and what is the likelihood of that class is this. So that class, okay, likelihood of that class is 2 over 12, and what is the uncertainty there? H01. Likelihood of this class is 4 over 12, and what is its uncertainty? H10, because it's all of them are 1, right? It's happening 1. This is 0. And then what is this event? This is full event. There are the probability of that event happening, that class happening, is 6 over 12. And what is its uncertainty? The entropy value, that is H2 over 6 and 4 over 6. Are you getting it? Okay. Now all these things, that's how we use it here. we continue to do the same thing. Among the observations, because this is over, this is the endpoints. Now, red means, not waiting. All the people who fall into it will not wait. Okay, that is, those who see none category of patterns, they will not wait. Those who see some category of pattern, they will wait. Those who see full category of patterns, it makes, certain probability of the people are going to wait. And that is what the first one is, not whether the bar is inside the restaurant or not, whether there is a reservation is needed, whether it's a Friday, raining, alternate restaurant is there, whether hungry or not, all those things don't matter. This is the first most important thing that will enter into the decision tree. This is the decision tree. Do you agree with me? Looks like a decision tree, everybody? And it's also called a tree. Okay, decision tree, right? Looks like a tree, right? These are the roots, or sometimes they say branch. These are the branches. Okay, so it starts with the pattern. It's upside down tree. These are the branches. Okay, all right. So among the people who are waiting, now I take only these people. How many people are there? Now I take only 6 people. Among these people, now I'm going to test what are the uncertainty, the maximum information gained where branches are. Among these 6 people only, these are over. Okay, among these people, 6 people only, and that is what will give me to calculate next level. That turns out to be wait time. Among these people who are willing to wait, where the patterns come, they look at the restaurant and it's full of, there is nobody there, they leave. Somebody is there, they wait. Definitely wait, right? But there are full people are there, so only some probabilities are waiting and some of them going away. And what is the next attribute that is important? It turns out to be the wait time. If somebody says 0 to 10 minutes, they will all wait. If somebody says, if the restaurant says no, there's going to be a 60 minutes wait, everybody will leave. People will wait partly, depending upon whether in probability they will be waiting. If it is 10 to 30 minutes or 30 to 60 minutes. If it is more than 60 minutes, nobody will wait. If there are less than 10 minutes, definitely all of them will wait. Do you understand now how it is going? The next step is going. Everybody answer. Do you understand? So here is the interesting question. As usual, Ishwaramurthy and Abhinesh said yes. Here is the interesting question. Okay. So, what is that S order of? What is meant by Dinesh? Order means what? Attribute available. Is that what you mean, order of? Yeah, the next attribute among the available attribute, next attribute to enter to guide us in the algorithm, like which attribute? Yeah, that is correct. Which attribute? That is correct. So the next attribute comes into play for creating the further divisions, developing further branches. Okay, these are called branches. Okay, for developing the next branch, the next collection of branch, weight estimate is the most important thing, and then comes out of that, these two cases are very clear. Only these two matters, 30 to 60 minutes and 10 to 30 minutes. So among the 30 to 60 minutes, what attribute to enter, right? So again, among the remaining observations, here there are 6 people only. So what are the people remain here? They are going into it for calculation. Okay, and all the things that turns out to be various variable, alternate turns out to be the maximum uncertainty reduction, maximum information gain. So that alternate restaurant is available nearby is what matters for them, for these people who are waiting 30 to 60 minutes. The same way for people who are willing to wait, when they heard 10 to 30 minutes, it depends on hungry. No other variable enters as the most important variable. So you keep doing this, and that develops a tree, branches, and that's why it's called a decision tree. So you can, I have it here in R also, okay, in R. So what I'm saying, there is a package called F selector, okay, F selector, feature selector. There's a package called feature selector. And that feature selector I can use, information. There is a function that feature selector has a function called information gain. So use it like this. You can use, unit of measurement, anything, but logarithm to the base 2 is what we use in, entropy measure, okay, entropy calculation. So you have to say the unit is equal to log 2, and then, target is, function of all the variables you are going to check it out. And then the results are, RES refers to the data set. This is the relationship, this is the data set, this is the unit of, uncertainty measurement, okay, base, log base 2. So all those weights are print weights. You can calculate all these things. You can see this one here, 0.541. Am I right? Pattern. So that's what I meant to know. It calculates all the things for you. You don't have to calculate yourself. 0.541. It turns out a pattern is the first best variable to enter. That's what we captured it. In a different way we said that. Now among the pattern is equal to full. Now we want to calculate the next level, right? And that is what is happening here, the next level. So among that variable, I run the model. I run this kind of information gain, and I see this one among the full. But I have to take among the full as well as because we know among the full is the one that is willing to wait, right? So among the full and one more condition I have to use to find out the next level for 30 to 60 minutes versus 10 to 30 minutes. Agree? Everybody understands? So we can actually use this method to figure that out, to do a complete decision tree. Are you with me? You don't have to calculate, man. You just do the R programming package. Excellent. Okay, very good. So let's take a break. So you know how to create a decision tree. That's all I want to conclude. Do you all know how to do a decision tree? So let's take a break. When you come back, I'm going to do random forest. Okay? Take 10 minutes break, everybody.
Sure. Got it, stop.
Yeah, I'm going to stop. Thanks a lot.
Thank you.
Me? Hello. Okay. So the problem is with the decision tree is that we are looking for one super learning algorithm. Get it? You can write it if you want. In the decision tree, if you build a decision tree, what we are saying is, no, there is one super learning algorithm, and that will solve the problem the best possible way. But that is not true. So what is true is, allow random samples as well as parts of the variables to pick up best decision in certain areas of the data space. Okay, so allow, what is the strategy? Next strategy is allow parts of samples or subsets of sample allow subsets of samples, sample observations, which means rows, right? Sample, which means rows in the data set, right? Rows and subsets of attributes, which means columns, right? Subsets of columns, attributes, to learn best, in its data space, Am I making sense? I have also typed it. Read that. Allow subsets of samples, that means rows, and subsets of attributes, that means columns, to learn best in its data space. Okay, because a subset of a column and subset of the rows is going to define only as part of the data space, right? Part of the data space. And in that data space, will it learn best? And can it better than the best decision tree that we have done? That combining such smaller decision trees combining such smaller decision trees, but many of them, will it beat the best decision tree that you can build? One big decision tree. That is the question. The answer is yes, always yes. In other words, a large number of small decision trees which are only marginally better than the random event together can beat the best decision tree. Please, if you want, you can copy this and you can keep it in your notes, okay? Because these are all well structured sentences, okay? Can beat the best single decision tree. Do you understand what I'm saying? A large number of small decision trees which are only marginally better than the random event together can beat the best single decision tree. So I can further add in between a large number of small decision trees in its data space, in its data region, okay? Even though they are only marginally better than the random event, together can be the best decision tree. Do you agree with me? Do you understand what I'm saying? Because whenever we do a random forest, we are always talking about regions of data space. Within that region that is defined by your rows and columns that you select. Columns means randomly you are selecting the attributes. Rows means you are randomly selecting the observations. Everybody gets it? This conclusion? It will beat. Okay, excellent. Now, it has a terminology. It's called, in random forest, it has a terminology. What is called the bagging and boost, bagging and boosting. Boosting, and I haven't introduced that yet. It's called random. The second randomization on the split of training and testing is also called bootstrapped samples, called bootstrap aggregation. Aggregate the results based on the bootstrap sample. So you are taking random samples, right? So it's not only rows you are selecting, but randomly selecting, in the training sample and test sample. Training, validation, testing, right? 3 parts, right? Remember that training, validation, testing, okay? Training and validation, and then testing. In the training and validation, you can again and again take samples and create a new type of training, validation, okay? That is called bootstrapped aggregation, and that's called bagging, okay? Everybody gets that? What is meant by bagging? So that is, that's a terminology devised at the time of developing the algorithm, actually, okay? So, but the main the mathematical purpose is this one. Do you see the highlighted one? A large number of small trees which are only marginally better than the random event together can beat the best decision single tree. Best single decision tree, okay? Best single decision tree. I repeated twice, decision unnecessary here, okay? And they found out that it beats, for example, there is 10 data sets, here, breast cancer data set, ionosphere, diabetes data set, glass, soybean letters, recognizing letters, satellite data set, shuttle data set, DNA, digit, all these things. The red one means single decision tree, and these are errors in the prediction, okay? The vertical axis is the error in prediction. Red one is, single decision tree, random forest is blue. So the lower the better. The lower the error is better. So the random forest is uniformly better than the single decision tree. There is a very famous paper called Statistical Modeling the Two Cultures by Brayman, and that is what introduced the machine learning as a starting point. Seriously, okay? And here is an example of Boston data set. it is available in mass package in R. So you are calling in library random forest, library mass. Mass has Boston data set. So you call in data Boston. Okay. The last column is your dependent variable. So it's a supervised algorithm. Last column is dependent variable. That is, but it is written in this case, first row, right? So just for the understanding purposes. Median value of income in thousands of dollars in Boston city. Median value, right? That is the 14th column, which is what the y variable is. All the other variables, explanatory variables, are all coded into X. That is the notation you have to use. All the 13 columns are coded into X. They are called explanatory variables. Y is the dependent variable. So you build the random forest. You can check the question mark random forest. It will tell you there's some details about the function, about the package. So random is all lowercase, forest F is uppercase. So when you do that, very simple, you just have to say random forest, okay? Random forest X comma Y, where Y is defined, X is defined, okay? Random forest, you just store it as an object under name RF. Print RF, this is what it does. Oh, you have asked for this function, random forest, X equal to X, Y is equal to Y. And type of random forest is regression because your variable is continuous. So there is also random forest can do. Here is the beautiful thing about random forest. Everybody, here is the beautiful thing about random forest, okay? That is, it can do the same algorithm can solve for both classification and regression. Okay? So what is meant by regression? A variable where outcome variable is continuous is called regression. Okay? A variable which is class, the outcome variable is called classification. So it figured that it is a regression problem, and the default number of trees built is 500. The default number of trees built is 500. That's a default setup. I don't have to say anything. I just have to call this. Boom, it's done. One small code. Number of trees, it builds 500 trees, and then the number of variables tried at each is 4. How many variables are here? 1, 2, there are 13 variables, right? There are 13 variables here. And the number of variables it selected is again, there is a default formula for this. Okay. The default formula is square root of P. Number of variables, you take the square root of that. Okay. Now, what is the square root of 13? It is between 3 and 4. Okay. So it satisfies that, and this is also for the continuous. For classification, that is the one. For continuous one, it is 2p. Okay, that's what people use. Not 2p. P over. Wait a minute. I have to give you that information. I'll tell you what that formula is later. Okay. So the number of variables tried in this case is 4. It's because there is a formula that connects. What is the default number of variables that the system will try. So it has taken 4 variables at a time. So you remember I said column wise it is going to select a subset of the attributes, and it says every time it builds a tree, it is selecting 4 attributes randomly. Okay, it is done after 500 trees are used, 500 trees are built, then we have to make a decision as to what is meant by correct, right, output. The way to do that is you run each of the observation in the test data set or even in the validation data set, run 500 trees and record the outcomes. 500 outcomes are there for the average price of the house, right? And in the case of continuous variables, regression, it's not difficult at all, right? You just take the average of those 500 trees. Okay. For each of the observation I said, right? Then you get the average price. That is your predicted price for that particular row, for that particular observation. Okay, but in the case of classification, you will find out, you will predict that class which has the maximum number of events predicted. Whatever this maximum number of events out of 500 trees, if there are 300 trees are predicted to be waiting and 200 trees are predicted to be not waiting, then you say for that particular observation it is predicted to be waiting. Do you understand what I'm saying? How the tree is used, everybody? Everybody? Oh. Anirudh says yes. Abhinesh says yes. Anirudh says yes. So in this case, we want to just check it out, how much variance explained, Dinesh says, can you repeat? Okay. So what I'm saying, so we build the random forest is built by the algorithm, and there are 500 algorithms, which is a default that takes, and then there is a formula that gives. I will give you that formula later. That formula tells you how many variables to use randomly for every decision tree. Okay, now 500 trees are built. How do we use this tree, the forest, to predict? See, in the case of tree, single decision tree, you know how to predict, correct? Give me the input. In the case of single decision tree, you know how to predict, correct? If it is one tree, everybody knows, very easy. If I have 5 trees, how will you do it? One tree will say, one tree will say, the individual will wait. The other tree will say not wait. The third tree will say wait. The fourth tree will say not wait. Fifth tree will say not wait. So 3 not wait, 2 wait. So the majority, it's called majority voting. So because 3 out of 5 said not waiting, it is predicted to be, for that observation, for that individual, it's predicted to be not waiting. Get it? Yeah, majority voting. So here is a very interesting way of seeing the graphics, how good it is, but you can actually calculate how much variance is explained by the predictions, right? See, for every observation, we know the total, for all the observations in validation set, we know the total variance. For all the observations in the validation set, we know the total variance. And we also know the variance that is the variance that is predicted by the model. So it says if the original variance is 1,000 units, 1,000 units of variance is there, and now 878 units are already captured by the predicted values. The predicted values have that much variance. So 87% of 87.84% of the total variance in the Boston median household income, median household value in thousands of dollars, 87. Whatever the variance there, out of that 87% is explained. So you need this kind of measurement. You remember how good it is? We do that in regression, right? So this is the goodness of it. So the other way to look at it is now we do the predict the function with the, so we plot this function. Look at this one. This part is first this part, okay? Plot predict RF. Okay, whatever the RF model is, the object is there, you predict that using this data, Y data. Okay, and plot the predicted values, outer bag estimation versus true values. So these are the true values. Okay, so we predict that for that data set, whatever the existing data set. So you didn't, you can change the data set also. In this case, the existing data set is I'm saying the new data set is X, but if you don't give anything, it will use the existing data set, whatever you have used, right? For that data set, you are comparing it with the prediction values of Y, actual values. And it looks like if you use the same data set, which is used for prediction, which is used for training purposes, if you use the same data set that you used for training purposes, then the prediction will be more accurate, isn't it? This is a new data set, because it's outer bag, which you did not use it. Outer bag refers to that sample which you did not use it. Okay, so you can see there is more variance here because you didn't use it, but X you already used it in the modeling, so it is going to predict well. It's basically the one where the training happened. So, but nonetheless, these are all ways to visually impress people, to say that how good your model is. Is that clear to you guys? There are a couple of terminologies I used here. One is out of bag estimation. That means the data set that you did not use out of bag. Okay. So when you use out of bag data to predict and compare, then there is going to be more variance unexplained, right? See, all over the observations are here. But this is the in bag. This is the one that you in the training that you used it for prediction and training. So it is going to have less variance here, and it is more on the lines of the perfect correlation. The line is the perfect correlation. This is the actual, the predicted data. This is the actual. Are you guys with me now? Can you understand what I'm saying? Anirudh says yes. Abhinesh says yes. You mean out of bag means not included? Yes, not included in samples. Okay. For training purposes, whatever is not used in the training purposes, it's called out of bag. Okay, remember. Sorry about the noise. Okay. I muted for a few seconds. Okay, the mean square error is average sum of squares of differences between actual and predicted median value. Okay, just remember that. Huh? So, similar to the entropy and information gain, the one that increases mean square error is the one that is going to be more useful to predict. Am I making sense? Inversely speaking, the one which decreases the variable, the attribute that will decrease the mean square error maximum is the one that is increase the maximum, increases the mean square error. So turns out to be there is a function called var importance, variable importance plot, var imp plot, RF. You build the you can build the model random forest and then just find out what is the one that is increasing the maximum, increasing the mean square error. It turns out that number of rooms is very, very important. Okay, the variance in the number of rooms is explaining the per annum forest more. Also, this is LSTAT. LSTAT means one second. LSTAT means here percent lower status population. Percent lower status population. If you have a percentage of lower status population distributed, that variance will increase the price in median price of households. Okay, and then the other one is next third variable important attribute is distance. Okay, so this means distance refers to distance to employment centers. So the more the variance in the distance to the employment center is going to explain more the housing prices. That's what it says. Does this make sense to you now, everybody? So you can do the variable importance plot to explain why the model makes sense to your management. Okay, good. Now, now I want to introduce what is called boosting. Okay, so the noise is coming. Okay, so the problem is, random forest can be biased. Okay, and also it will take a long time to converge. So people have invented a method called boosting. That is, in the solution space and the solution pathway. Now I'm using the word pathway. Okay, the solution pathway can be reached more efficiently if you use what is called the boosting method. What does that mean? It means you go in the direction of the search of the next tree. You remember, we have to combine the trees, right? You have 500 trees, but you are just taking the majority result. Okay, that's what we are saying. That's the first strategy in the random forest. You do lots of little trees, which is, little trees means weak learners, not one super learner, which is the one big best decision tree. Weak learners are the little trees that are, large number of small trees. When I said that, right, for random forest, your strategy is large number of small trees, and those small trees are, each one is called a weak learner because it's a small tree. It can only learn a little bit, but it will learn a little bit better than the random in a certain region of the data space. And boosting reduces the bias of the weak learners by prioritizing and moving in the direction of different parts of the instance space where more evidence is unaccounted for. So when you combine the decision trees, which means one tree, you are building into the output of one tree into the next tree, or next, not even a next tree, next cut within a decision tree, next cut you are going after. Okay, next layer. So what we are saying is that boosting is telling you, so you create a entry point, and then that entry point does not explain certain observations, and now you are going to look at the next split, not purely information gain, but boosted information gain. Okay, by that what we mean is we are going to bring in the next decision tree. Actually, it's a cut, and I don't want to say the decision tree, I keep saying this word. The next entry into the decision tree, a particular decision tree, is going to be one where the unaccounted observations are given more weights, unexplained observations are given more weight, or misclassified observations are given more weight, so that the tree will learn better, faster and better. Am I making sense? It is about in the direction of the unexplained part. The search path is moving in the direction of most unexplained part within that particular data region. Are you with me? See, every decision tree is done by random selection of attributes and random selection of observation, which defines a certain data space segment. And that is, we are trying to build the best decision tree with that particular segment. And we accumulate them for prediction eventually. Certainty paths are taken for granted. Certainty paths are taken for granted. It's still not clear to me. I'm saying wherever it is not explaining, we are the next split, next tree, both of them, I'm saying next tree and next split will move in the direction of where maximum unexplained parts are, maximum errors are. I'm going to give you Adaboost pretty soon. Hold on a second. That's where I'm going right now. Okay, you will learn that what I'm saying. Okay, so I have what is called 1 second. So this method is called adaptive boosting. That is, we the algorithm adaptively moves in the direction of reducing the mispredictions. Wherever mispredicted most, that is the direction it is going to move. That's what I'm trying to say. Am I making sense this time better, Dinesh? Wherever it is predicting not properly, that is the direction it wants to move and do a better job. Okay, and there is a way to do that. And so here is let me take this example for you. Adaboosting, and that method is called Adaboosting. There are many different boosting methods, and we are going to go first look at what is called Adaboosting. Okay. Okay. All right. Here there is. All right. Okay. Let me see. I think I might have it here in this one. Adaboost. Okay. I should have a separate workbook here. Okay. Okay, where is that one? Yeah, here it is. So let's consider this example. The example is as follows. Oh, I may have to go here also. One moment, please. I think I should go here first. Okay. So these are the 10 observations actually, right? 1, 2, 3, 4, 5. 5 plus 5 negatives, right? 5 plus categories and 5 negative categories. They are distributed like this. First observation takes 1, 5. Okay, so you call it as 1, 5. This is 5, let's say. Okay, this is second observation is 2, 3. Third observation is 3, 2. Everybody understands this? This is 3, 6. This is 4, 8. This is 5, 10. This is 6, 8. This is 6, 6, 6 maybe. Okay, 6, 6. This is 7, 8. This is 8, 8, 9. 9, 3 and 9, 9. Everybody understands these points? And this is the two-dimensional point. And these are all pluses. These are all negatives. Do you understand this point? The data points well? Okay. Ishwaramurthy says yes. Okay, good. Then it says yes. So the what we want to do is we want to find out this rule. This rule we want to find out. Okay, this rule we want to find out. That is the one that clearly separates these plus and minus. Okay. So a good classification is one. In this case, is this one. Now, what we want to do is first we want to use this x-axis. H refers to the rule, simple rule, right? Left or right, left or right. That's the only thing, right? Each decision tree in this case is what is called a stump. That means left or right. A variable considered, and that variable is to the left or to the right. That is called a stump. That is also a decision tree, very basic decision tree. Do you agree with me? Yes, stumps are basic decision tree. fundamental decision tree, foundation tree. You can't get more simpler than that. Okay, so first we walk from here all the way systematically to the right on the first axis, and then I say, okay, I put a step here because afterwards I'm getting confused here. So here I see 20%, 100% of 20% in this case, right? 100% of not 20%, 100% of the 40% of the plus are completely identified here. There is no confusion here. There is no error here. Everybody gets it? So to the left is plus, to the right is, to the left is plus, to the right is not plus. You can say that way. Okay. So that is the error here, but this is certainty. Now we want to continue to move in the same direction, but the problem here is that there are 3 of them are pluses, 5 of them are negative, right? So my goal is to find out this plus, right? The target is plus, and my goal is to find out the plus. But these are misclassified. So what I am trying to say is I'm going to give more weights to these things. So look at this, I made it into bigger pluses. That's what giving more weights into. So the algorithm will see this quickly, more than this. It will see in its path, in its vision, in its search for, in its mission to search for this, it will see these pluses more easily by when I give them more weights. Do you agree with me? That is what the weight means here. That means I give more weights so they get prominence, so the algorithm can see this than this. In fact, in terms of the weights, if I calculate these 3 weights, it will overcome these 5 weights like that. Are you with me? So we are going to find out a mathematical method to assign weights. Everybody's with me? Yes? 1 yes, 2. Very important step I said. So you all have to say yes or no. Thank you, Abhinesh. Anirudh, thank you. This, okay, all right. So something is happening, immediately. There are data points here. These are all, the data points are given by these values I told. So these are all data points here, right? I told you these are data points. That's why the scales are given 1 to 10, 1 to 10, right? These are data points. That data point introduces a possibility for me to stop here, and I call this as the first decision tree based on H1, and that creates an error of 30%. In the case of the overall, how many errors are there? To the right is minus, to the left is plus. That's what we are saying. Not plus means actually minus, right? Which is same as saying minus. So 100% of the minus are identified. 40%. 100% of the minus are identified. 40% of the 40% of the pluses are identified to the left. 30% to the total. 30% of the total, which is 60% of the pluses, right? 30% of the total is error. Do you agree with me? That is what epsilon 1 the error is. Okay, but there is some calculation I'm going to do. I'm going to create a weighting process. Accordingly, I get another constant called alpha 1, which is 0.42. That will give certain weights to these things. And I'm going to explain to you how to get this. Hang in there. That is step 2. Okay. First is done. So at the end of the first step, I've identified which of the observations need to be given what weight. Okay. But because so much weight is here, they will be identified in the next search. I will end up coming up to this here. I will say to the left is, because together, all these things together, overweigh compared to these minuses. So this says, H2 says to the left of that is plus, to the right is minus. That's what it says, H2. And now all the pluses are identified correctly, but there are 3 of them are misidentified incorrectly on the left. Everybody is good with me? So what do? I give more weights for those negatives. I already have given some weights here, but now I give more weights for these guys to get identified correctly. But I have already exhausted all these things on the x-axis. So now, horizontal axis. So now I'm going to search on the vertical axis. That's what I'm doing here in the next step. In the vertical axis, if I put If I find another H3 here, to the below is negative, to the above is positive. Remember, these are all the cases which are already identified with a different stump. So now I have to combine 3 different stumps. If I combine those 3 different stumps, then I have solved the problem. And that stump says to the left of this, first stump says this, to the left of this is plus, to the right is minus. And then the second stump says above this, to the right of this is negative, to the left is positive. So third stump says to the above this is positive, to the below is the negative. We want to combine these things piecewise. We want to combine these things piecewise because this is, for this region, we don't want to use this, the original first stump, S1 stump. Do you agree with me? But when I am applying the third application, I don't need to apply the first one all the way up to the third. This part I don't have to apply. This part I don't have to apply when I selected the H1. Do you agree with me? So combining means I have to combine piecewise. Are you with me? Combining, okay, Anirudh says yes. Combining all the stumps, right? All the stumps means, please write it down, means I have to combine piecewise. Everybody agrees? I think everybody said yes, okay, before I could complete the typing. Okay, so and in the process that is done using this computational method 0.136. So I'm going to get all these calculations done for you momentarily, okay? But you see the logic here. So when I combine that, the result will be like what I started was what I planned to achieve. The plan to achieve was this one. You remember the plan to achieve is this, go up to this, go up to this, go up to this. And the combination, piecewise this initially we saw this one, this line, and then we saw this line, and then we saw this one, right? So let me draw and show it to you. Maybe I will use the red one. So initially, I don't know, I don't think it's going to work. Oh, okay, it is working. Initially we saw like this, saw like this, right? So piecewise means this part only, this part only, and this part only. That's what piecewise, combining piecewise means. Everybody is good? So if my algorithmic method accomplishes that, developing all these H1, H2, H3, which are dependent on epsilon 1, epsilon 2, epsilon 3, alpha 1, alpha 2, alpha 3, and then combine them eventually piecewise, then I have solved the problem. Agreed? Okay, good. All right, so I'm going to show you the method here. That's what this one is. So here is the workbook. Again, I'm showing you those things here. Okay, here is the workbook. So 1 comma, you remember that 1 comma 5, 2 comma 3, 3 comma 2, these are the things, 8 comma 5, 8 comma 8, and so on. Okay, and these are the classifications, right? This first point is the plus, second point is plus, third point is minus, fourth point is minus, fifth point is plus, sixth point is plus, seventh point minus, eighth point is plus, ninth point is minus, 10th point is minus, right? These are the classes. And these are the data points. These are data points, these are the classes. These are the dependent variable, these are the independent variable. So each observation has a weight of 1/10 because there are 10 observations, each has a weight of 1/10, right? 0.1, 0.1, 0.1, 0.1. So when I say, I will give weights in the direction of misclassified observation, I'm going to, increase the misclassified observations and decrease, because where am I going to collect the weights from? I have only a total weight of 1, right? I will borrow from here to distribute it here, because certain observations are identified correctly. I don't have to worry about them. Okay, are you with me? That is the strategy clear? So these are the 3 points which are misclassified. That is the 5th observation, 6th observation, and the 8th observation. Understood? Maybe I'll put this one, insert rows. That might help. So this is the observation number. 1, 2. So the 5th observation, 6th observation, and 8th observation are misclassified. That is what the graph that I was showing you earlier, right? Let me go back again, right here. So this is the 5th, 1, 2, 3, 4, 5th observation, 6th observation, and this is the 8th observation. This is 7th and 8th. Everybody gets it? These are misclassified observations. That's what we are addressing here, okay? So what we are saying is, now, if I have a calculation mechanism by which these weights are increased, these weights are, I borrow from there to increase these weights, I'm good. That's the point, okay? So how do I do that? There is a formula method, okay? There is a formula method that I'm going to share with you. Here it is. Here it is. It may look like a very, 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 very hairy, okay, but very simple. What is the first time? What is the error we have? 0.3. You remember that one? So I know this computational quantity, right? So alpha is defined like this: half of logarithm of natural logarithm of 1 minus error divided by error. Everybody gets this point? This is easy to calculate now, right? Once I know the epsilon t, yes or no? Anirudh says yes, Yeshwamurthy says yes, okay? So once I know the errors, I can calculate alpha t, okay? Because I'm going to use the alpha t to boost the weights, okay? So this is the hypothesis weight, and then we use the hypothesis weight to boost the observation based on whether it is misclassified or correctly classified. See, for the correctly classified, I'm reducing the weights, e power minus alpha t. For the misclassified, this was not equal to y, means these are the error prediction, right? Those which are incorrect, I boost the weights here. Do you see what I'm doing exactly, everybody? Very simple, right? But how the heck these guys got this specific formula? Well, it takes years sometimes. So don't worry about it. Oh my goodness, I can't do this kind of things. Don't think like that. If you invest your time, years, sometimes it takes years, decades sometimes. So don't worry about it. But the errors are coming, epsilon t's are coming from the errors of misclassified. The misclassified error boosted, misclassified error is boosted by this transformed value here. There is a reason why you come up with this. You are saying basically, it's also called odds, right? If you look at its odds, you are giving 50% of the odds for the boosting coefficient. Okay, 50% of the odds for the boosting coefficient, logarithm of odds, right, for the boosting coefficient. So this is e power minus alpha, means you are reducing the weights there and increasing the weight here. But then once you increase and reduce the weights, you want to normalize it so that it becomes 1. That's what this is all about. Okay, this is all about. This is just normalization. Okay, so what does that mean in terms of our calculation method? Take a look at that. So I have here 0.3 alpha 1, epsilon 1 is 0.3, so I can calculate alpha 1. Everybody understand? Everybody agrees with me? Now I need to calculate epsilon 2. So for now you don't have to worry about it. This is about convergence. Don't worry about it. It tells you how quickly it converges. Don't worry about it. Okay. So what we are saying is that so this is done. I have boosted it. Now for the boosted weights, this is our boosted weights, right? This is our boosted weights in the direction of misclassified observation. Dinesh, do you get it now? I'm boosting the weights in the direction of misclassified observation. Only in that those things need to be correctly classified. That's my worry. So now I apply the same thing. So in the second attempt, you remember that H1, I keep moving in the H direction. I found out the last, somewhere, actually, somewhere here, I can go back and show you. I keep going until I go, next time I kind of, H2 is, I keep going until I see 100% of this, 100% of this are misclassified classification, misclassified observation, the plus are identified now, including the previous one, right? So I want to make sure that these are correctly classified. So H2 will do that for me. But then there are errors on the minus side. Now I boost the minus one. That is what I'm going to do. So let's go back to this operation again. So in the next time what happens? This is the, see, this turned out to be 30% only because this is a misclassified point for probability 0.1, 0.1, 0.1, so 0.3. But here it is, this time these three observations are misclassified. The 7, 4 and 3 are misclassified. Everybody understands? That is this one. Think very carefully. These are misclassified. These are 4, 5 and 7. Okay, everybody is good. And they get, remember their errors are this much, right? 0.07, 0.07, 0.0. So their misclassified error is 0.21 this time. Everybody gets how I got the 0.21. This time, the second iteration, I got 0.21 error. Ishwaramurthy says yes, excellent. Anirudh, Dinesh, Abhinesh. Abhinesh says yes, excellent. Anirudh says yes. So the moment I know epsilon 3, I know how to calculate the alpha 3, right? You remember that? Half logarithm of 1 minus epsilon divided by epsilon, right? That is what alpha 3 is. And alpha 2 for now, right now, alpha 2. So I can calculate alpha 2. So which means I can calculate D2 also. You remember that one? But we'll come to that. D2. D2 is needed for the convergence. No, normalization. No, D2 is needed for the normalization. Okay, remember that. No, not just the convergence alone. So D2 is done. D2 is done. D3 is needed. Now D3 is calculated. I boost all of the observation, misclassified observation by epsilon minus alpha 2. I'm sorry, epsilon plus alpha 2, misclassified observation, correctly classified observation, epsilon minus, exponential of minus alpha 2. Everybody gets it? What I'm saying? So let me write down. Boost the once I know epsilon, I know how to calculate alpha. Correct? Once I know alpha, I standardize it, normalize it to get D2, D values, okay? D values. Everybody gets it? And that will help me to boost the weights or reduce the weights, depending upon whether they are misclassified or not. Okay, that is the process. I continuously keep doing it until all of them are identified correctly. In the third step, everything will be identified correctly. That is the point. Okay, so you can see that, this is the third step. I get epsilon error is 0.13 because these are the misclassified, and then alpha 3 is 9.2. But by that time, when I combine all of them in a piecewise manner, in this case, like this, then all of them are 100% identified. So the algorithm stops. very interestingly, this Adaboost, this is called adaptive boosting. Okay, it doesn't over predict. That is the very beautiful part. It just so happens it works very nicely. Okay, now there is another example that I will leave it to you in the lab class to do it in the lab class. Okay, so here is I think I have it. What is called the restaurant visits, Adaboost, not assignment. No, assignment for Adaboost is not. I added few more points for you to do the work. Okay, Supriya, are you there? Hopefully you are listening to this. Okay, so we can give. Are you there? I can't.
Yes, sir.
Yeah. Okay. Fine.
Yes, sir.
So we will give this Adaboost with extra observations. Okay, for the lab class we can do. But is that clear to you how the Adaboost is achieved? It's all about, in this example, it's all about stumps. Left or right, left or right, left or right. Most of the times, that is what happens in Adaboosting. Very simple stumps are used in Adaboost, even in a multidimensional space. Okay. So that is about Adaboosting. But there is also gradient boosting, and there is gradient boosting as well as extreme boosting. Okay, so I'm going to talk to you. Any questions here? Because I'm going to introduce you now gradient boosting and extreme boosting. Yeah, here is the calculation worksheet. Okay, that's okay. This is exactly what I did. Same worksheet. So let's do a case study in. How about we do a case study in Adaboost? Okay, so I'm going to do the bank data. It's available in downloads. I hope it is there now. Let's run this one, RStudio. You can redo this, in your lab also, but let me, walk through this example. So maybe it's there in here. 1 second. Okay, we will do a new one. That's okay. That's what it is. Markdown. Okay. Adaboost. You don't want here, you want to go into here, okay. So install all the packages that are needed. It says, okay, I said fine. So the new version of RStudio tells you what are the packages missing. Okay, so that's good. So let's read the data. You can read the data with zip file. Actually, the R can do that. Unzip condition, you can do that. So it has. He didn't read, so maybe it's. I don't have it. Let me check. Downloads. Bank.zip. So the folder is not there. The bank.zip is not there. Okay. So one second. I think I know where it is. I just need to put it. Bring it from a different hard drive. I'm going to go. Let's see. I hope it won't crash my system. My whole system is failing. I'm using it right now. That's the one I'm using it right now. As I change things, it may give me trouble. Okay. So I'm searching in this new drive, bank.zip. I know it is there in the download folder. I copied it here. So I don't want to search all over. There is something called download. Oh, I'll go there. Downloads, yeah. So it should be here rather than searching all over. 1223 downloads. I think it's better that I look at this one. It's not there. Oh, gee. So maybe here, back. Okay, there you go, back.zip. So let me move that file to this one. Okay, it's here. Bank zip is there, so it should work now. Let's go there. Try to do that again. All right, it ran the data. Okay, so structure, for example, add the data, Adaboost data. I call it as add a data. Okay, so it has what? 2 observations are 17 variables. Really? Closing unused connection 3. That's okay. Added data. It has a large data set. Something is not correct. Let me go back and show it to you. So bank full bank. This is a short version. This is a full version. Okay. So there's a lot of data there, but I'm not reading it correctly. So that's the reason. Okay. But it does say bank.csv. That's a file to read. Read unz. So let me read this one. Maybe that's not correct. Let's see. Structure. This time I'm going to put the same thing. Let's see what happens. There is some issue. Okay, there you go. So I took a smaller file, bank.zip, not so there is a bank underscore full versus bank dot CSV versus bank underscore full dot CSV. I took the smaller file just to show you the example. So there are 17 variables, 4,521 observations are there. Okay. So I'm going to take this one out. It is repeated. I don't need that. Okay. So let me run it one more time and put that structure command here itself. Okay. This is the old one. So I can't even type it now. The D key is and I have to press it very hard. Okay, here is one more time. I'm reading it. There you go. Okay. So I got 4,521. Now, there are 17 variables are there. Age of the person who took the loan, what is the job of the person, what is the marital status of the person, education level of the person, whether he has defaulted in the past, balance, how much balance, housing, does he have housing, loan, contact, all these things, okay? So let's do the Adaboost model first. So what we are saying, boosting, there is a function called boosting, okay? In that package, Adabag package. The Adabag package has a function boosting, it will do the work for you. And y, which is the factor which is a level yes or no to predict whether he can be given a bank loan or not. Okay, so some kind of a credit problem, credit reserve problem. Okay, so and then based on all these variables. Okay, data is added data, boosting true, yes. Final is 20 steps, M final. Coefficient of learning is Bryman method. So there are different methods are there. Coefficient to learn, Bryman uses derivatives. Okay, first derivative and second derivative. So use that and then build the model and see what is the summary of that model is. That's what we are going to do right now. Okay, so let's run it. So it is looking for the Adabag, loading it. So that's what is going on here. Okay, R part, caret, all those things. And then it is building the model right now. This part is working, building the model. It is still working. See, that's the reason why I put a small, small size of data, okay, rather than bigger one. So, okay, this is the summary. It's basically, formula is, trees, 20, you built 20 trees, okay. Weights is 20, only 20 trees, 20 weights. Votes is, these are the probabilities and votes, so many different possible combinations. Then importance variables and then terms. Okay, so let's build we have built the model. Let's go after the trees. Just let's see what those trees mean. Okay. This is the tree. Okay. You can read this. It's not a very difficult tree to read. It tells you exactly what they mean. So the root is 451 and 2,258 out of them are no. With remaining is yes. Okay. So 2,258 are no's, and that is 49.9%. The remaining is yes. Age greater than 25.5, has 4,368 yes. I mean, the 4,368 is total. Out of that, 2,141 is no. Within that category, married, single, has no 1,818. This category has 3,841. Out of that, 1,818 is no category. And then you add to that the duration, whatever that duration variable is, less than 123.5, If that group has 404, out of that 128 is no, that is 31%. Okay. And then the greater than 123.5, the duration greater than or equal to 123.5 has this many number of observations total, and this is no. And then add to that this condition. Job is entrepreneur or housemaid or management or retired or self-employed or student or technician or unemployed. That category, this subcategory, all these things combines subcategory 2180. 180. Out of that, 1005 have no category. So likewise, you keep doing all these things. You can see that various levels are done. And then the other one is age. What is this one? Age greater than 25.5, right? So the next comes age less than 25.5, and that's what this one is. So you see a complete tree here. It's a boosted tree. That is the only thing you have to remember that. Remember that, huh? It's a boosted tree. Everybody gets it? Now I can find out the weights at various, the weights. These are the weights that happen at every level, right? Split level. One. Okay, so these are the weights, and then the importance. You can see that age is having 5.3751, and balance is 8.174 and so on. Okay, marital status month, P days, P outcome, previous, and so on here. Okay, these are the weights that are coming out. The error values are given here for the model. Error evaluation, error evolution, not evaluation, evolution. And then you can use the predict function to predict based on the model that we have built with the added data. We are using the same data set. So I can actually extract each of the single trees. Okay, here is an example. Just the first tree alone. I can do that. T1. The whole tree, only one we built. Okay. What about Adaboost 1? And let's plot the tree. Plot T1. Plot new. Margins too wide. I don't know. Plot. It says margin is too wide. Margin is too large. We'll figure that out. Okay. Plot tree text. Pretty. I thought I did last time. No tree. Okay. Because we didn't do that. We didn't want. So here is the prediction. Let's just predict that for added data that we used. It can be a new data also, but we are using the same data here. I'm not going to use all of them to print here. Let's just take the head category. Okay, so it's actually an object. So let's first find out what are the members of this. So we have class, confusion matrix, error, formula, probability, and votes. So how about we do this confusion? Not ls this time. I should not say ls. Predict $. Confusion. Okay, there you go. So we have, so what is the accuracy here? 3,939 plus 352 divided by 4,000. These are all the predicted classes. So it just predicted, when I said here, the only top 4 parts, 5, 4 or 6, it printed 4, 6, all of them. Okay. So the structure, we saw that. Number, we can just say Andrew. Data. Oh, data. Add data. Oh, data. I don't want boost. 4,521. So out of that, so the accuracy is just to show you the calculation. Okay, 39 plus 352 divided by 4.21. So 94% accuracy. Okay. But out of the S category, it did a very good job, right? 352 divided by observed class is this one, right? 169. It's a column wise. You don't use column, the actual. It is actually predicted is usually for me column, but here they used it differently. So 352. This is what the target class prediction, okay, per percentage of prediction. 67% accuracy. Recall here is 67%. When the actual S class is out of 169, out of the total sample, it is 169 plus 352 divided by the total 4521, right? It's only 11%. Out of that 11%, so you are not comparing with 50%. It's only imbalanced data. So 11%, you are able to predict 67% of the 11%. That's a great because if you do randomly, it will be at best 11%, right? Random prediction. But no, our model predicts 67% of 11%. Okay, which is pretty high. Okay, so this is how you can use R and you understand how to do Adaboost, but that is only one of them. Okay, so there is also some references here about the notes, about the data set. So let's go continue. Oh, it's 11 o'clock now. Okay, so in the next class, I'm going to teach you about gradient boosting and very importantly, XGBoost, because that is a competition winning boosting method used more often and more times one in the competition. Okay, so very, very important. We will cover that in the next class. And tomorrow I will finish that one, boosting and possibly gradient boosting and XGBoost. With that, we can move to the second half. Most likely, the second half I will move to neural network. Okay. Any questions? So here, you are being asked to think differently, very different ideas compared to statistical learning. There are no type 1 error, type 2 error, all those things. We just look for the confusion matrix, the best performing confusion matrix on a test data set is what matters to us, nothing else. Okay, can you email the whole deck? I'm going to give you the link. Okay, I'll do that right now. Yes, I'll do that. I'll give you a link for everybody. I'll CC that to Supriya also.
Yes, sir.
No, I'll do one thing. I'll give it to you, Supriya. You can. I still don't have. See, we used to differently. We do the things. So you have the link. You have the emails with them. So you pass it along with them. Okay.
Right, sir.
Okay. Thank you very much.
No problem.
Yeah, go ahead.
No, that's it. Nothing.
Any questions?
Tomorrow is the same lecture only, right? No practicals as of now.
We will go through an example like this.
Okay.
Just to connect. Otherwise, because there is a lot of theory going on here. In fact, tomorrow is going to be a very complex, but I hope to explain, I hope to capture their imagination so they can appreciate it, but we'll see. Okay, we do this all the time. It's not anything new. For the first time, I'm not doing it.
Okay.
So I will do that.
Yeah.
How the extreme boosting is constructed, why it works. Okay, and then I'll go through an example. Afterwards, I will do
Fine.
the neural networks. That's our purpose. Okay, and tomorrow I'll try to finish
Okay.
also basics. Thank you.
Thank you,
Bye,
sir.
everybody.
Bye. Have a nice day.
You too, everyone.